Thank you so much, Sadar, and thank you. And good morning, University of Victoria. Okay, I want to thank you for taking time to watch this presentation. Questions, comments, concerns, orchids, onions, whatever you want to throw at me, put it in the chat line, or you can raise it because actually we're a fairly small group here. Okay, so what we're going to be talking about today is where we see the niche for mass timber construction in our realm. And mass timber, I'm speaking predominantly of hybrid buildings. So we're going to be talking about that. We're going to be looking at how this product is actually installed. And we're going to be using as an example a project that you can see here, University of BC, UBC Gateway. And we're also going to be using UBC Gateway as a bit of a case history and talk about some of the issues surrounding composite beam design. Okay, what we're doing here is looking at mass timber hybrid buildings, and the materials that we use is not concrete only, not wood only, not steel only. It's a combination of all three. And you can see there's some examples of that there. Our key design philosophy here is to put together a one-stop structure shop. That's essentially what we're looking at here. And the value comes into a uniform system, predominantly of connectors. So we're looking at that, and here are the four key attributes: safety, speed, space, and sustainability. Space is the big issue that you have with mass timber design. And I'd say that close behind it is the connections between beams and columns is a predominant area, and we're going to be dealing with that quite a bit. Okay, now I have to go south of the States here to the American Building Code for a moment. They're building type 4, A, B, C, and HT. This is what we see as the sweet spot, okay, for mass timber design, above 6 stories, up to about 16, 18 stories. That is where we see the optimization of this kind of hybrid building design being most effective throughout, say, Vancouver Island, particularly around Langford area. So hybrid structures, basically any deck type is acceptable. CLT, DLT, NLT can all be used and supported by any type of column. We show wood here, could be wide flange, could be HSS, could be composite columns. What we're going to be focusing predominantly on, though, is TCC, timber concrete composite. So this picture that we're showing you here to start the installation process is not an older building on Yates Street in Victoria. This is a brand new project. And if you look carefully, you can see one of the hallmarks of the design right here. The spacing between these columns is actually 9 by 9. And you can see here, the main structural beam is actually buried in the floor. The architect didn't like my beautiful gray color, so he covered it up with a wood panel. So the installation of composite beams is pretty straightforward. It's always considered a gravity system. And one of the hallmarks of the gravity system here is the connections that fall over the top of the beam. So what we're doing is taking technology from big box stores and applying it to mass timber buildings in multi-level. This picture tells another 1,000 words when you look carefully here, and you can see this composite beam here. The downturn is about 75 millimeters, not 3 inches. Whereas look here, this edge beam, this glulam beam, is about 1 meter deep. So that's gives you a relative difference in the carrying capacity and the depth required. Now, this is a large circular donut-shaped building. No, it is not the new headquarters for Tim Hortons Donuts. It's actually a shoe manufacturing plant in Austria. Now, what we see here is a relatively short span between columns. It's actually 3 meters. The reason for that is that these are all segments of the circle. And we use teleposts here, but I don't want you to have the 28D concrete cure attack as you have with cast in place concrete. No, these posts are only designed to stay in place for approximately 5 to 6 days. Once the concrete reaches about 60 to 70% strength, you can remove the shoring. On top here, what we're looking at is the concrete slab. And this is straight goods right out of the back of any pump truck, any mixer truck throughout North America. And you can see here the mesh and then rebar. The mesh is tying the concrete all together, of course, and the rebar ties the composite beams into the concrete. And then the concrete's pumped and poured in place. Now, the concrete, straight goods, about 4,500 PSI, 7-inch slump, 1/2-inch granular. So the reason for the high slump like that is to flow into that beam, because that beam is completely integrated into the slab. So here is what you end up with. When you look here, this building here, notice lots of daylighting, lots of open spaces. So this becomes every interior office designer's dream, to be able to take this building and do whatever you want with it, and even reuse it. Now, I've also showed a picture of another building similar that's part of the same campus. So again, the hallmark, about 9 meters between the columns. And you can see here the mesh. This mesh ties the concrete topping to the wood deck below. And you can see here, mechanical, electrical, plumbing started to be put into place. Now, I'd like you to keep this picture in the back of your mind, because we're going to come back to it with new and improved designs. So the technology for this is rapidly changing. So now we're going to be starting to look at the takeaways from what we're talking about here. Yes, I know that we have some German here. I've decided to leave it for the time being. Now, what you see here is the comparison of the attributes of timber concrete composite on the right-hand side versus straight wood. And straight wood deck design has been the most common design because it's all promoted by timber councils throughout Canada and the United States. But as you can see here, look at the attributes. We're looking at about a 30-foot span versus here a 20-foot span. Now, for student residences and apartment buildings or entry-level apartment buildings, this could be perfectly fine. But for office structures, owner-occupied buildings, this is by far the preferred choice. So now let's have a closer look at some of the hallmarks of that. So here you see here, composite deck design, where the mechanical, electrical, plumbing can go wherever it needs to go. You can see the cable tray here versus this here. Now, what you don't see here is the huge expense associated with this kind of work, because this building here is a tenant improvement. Okay, so the building was originally designed to be beautiful, gorgeous, with massive drop glulam beams about a meter deep. And you can see here the tenant has had to put the HVAC system in. So that's an extra engineering cost. And you can see headroom issues, bulkhead issues, cosmetic issues. And you can see here where the hole was put into the beam by the CNC machine of the glulam manufacturer, and now it's not required. So mechanical systems change, building design changes, and you're stuck with that for the life of the building. Okay, another key takeaway is that we have the opportunity to reduce the building height. Now, why is that so important? Because building owners certainly think about it, architects may or may not think about it, and structure engineers notoriously never think about it. Well, they do sometimes. Okay, so let's have a look at that. And we have to learn from the center of the universe called Toronto. Sorry, guys, it's not Victoria in this case. So in Toronto, what happened on this project is that the architect and engineer submitted the design to the City of Toronto for a building permit. They got the building permit, but in that process, they came to the conclusion that they could enhance the design of this building. And you can see the technical parameters here, pretty straight goods for a mass timber office project. However, the occupancy load was lighter than what was desirable. So they redesigned the building, and they went from what you see here, just over 4 feet, or about 1,200 meters, 1,220, just over 4 feet to just over a foot. So what's happened is that they have compressed that structure depth by about 20 or about 75%. So now let's have a look at the ramifications of that. The architect then went back to the developer and said, hey, look, we can reduce your building height by over 7 meters. Now, the developer said, wait a minute. In that part of the City of Toronto, we do not have to reduce building height. We don't have a height restriction. Yeah, but you can still do it. The developer said, no. What we are going to do is add 2 more floors to the building design. So instead of 8 floors, they're getting 10 floors. So they're getting extra value. 2 more floors are added to the overall building design. So let's have a look at that proposition. Okay, now in downtown Toronto, the wall area per floor is 2,080 square feet. The cost for curtain wall in downtown Toronto is $290,000. The floor area, 20,400 square feet. So you know where I'm going with this. We're going to figure out the cost per square foot, which turns out to be $14. Now, that certainly grabs the developer's attention. Yes, but what really warms the cockles of his heart is right here. $2.3 million is what he could have saved if he had taken that building height reduction. Now, that is just for the cladding alone. That has nothing to do with the elevator shafts, the stairwells, mechanical, electrical, all the vertical risers. So I would hazard a guess it's probably double that. But he said no, he is going to keep the building the same height and get a 20% increase in the revenue by adding 2 more floors. So now you can see how developers are starting to look at this kind of an assembly and say, do we really need to have a 4-foot floor assembly? Okay, another key takeaway here is looking at composite beam design when you look at compared to, say, point load system. So what we're looking at here, this is a typical detail from a point load system. Now, what you don't realize here is that the amount of hours that are taken in coordinating all of the trades to work around this kind of an assembly, fabrication, installation, on-site delays, and here, repair. These are all issues that are not usually taken into account, at least the full depth of account, at the first go-around on the design table. So we'll show you how this all comes together right here. Yes, this is a very busy slide, but there's some very important information here. What we're looking at with the slim floor assembly, what you have here, up to 30 by 30, is your base spacing, okay? You're limited to about 12 by 16 right here with point load. If you go to straight CLT, you're approximately 30 by 16. So you can see you have a lot bigger, greater open space here. Column volume, now we're starting to get into it. You have far more columns, roughly twice the number of columns. So that factors into fire code design also. So the char rate becomes tremendously important right there for columns. On wood deck here, with composite beam design, any deck type, CLT, DLT, MMP, TCC, whatever you want to use, you can use with this kind of an assembly. Over here, you are limited to CLT. And CLT is the lowest common denominator of wood deck design. Okay, that's the basis. Everybody can make it, but not everybody does a very good job at it. Okay, now, here's where we really get into it. Beam becomes its own loading system. So when you're doing your design models here, the composite beams can take this axle loading and transfer it back to the elevator core. So this is part of the earthquake design that you have to think about, particularly on Vancouver Island. Now, I put over here, point load system. Whoa, look at that. Do you remember that little connector that we saw right here? That little connector is difficult to design for seismic, number one. And number two, it costs about $1,500 a unit. So you don't think about that when you think of mass timber and point load. But it's a very expensive proposition when you start to factor in all the auxiliary costs. Okay, guiding here, beam design. What we can do here is have transfer beams built into the assembly so the building facade can move in or move out. Okay, you can cantilever out, you can go back in. With mass timber point load systems, straight line all the way down. So the building facade remains exactly the same. Now, fire. Okay, here we start to get really interesting. The beam itself that you see here, the pictures of, has a fire rating up to 4 hours. And that's a ULI, ULC fire rating. With point load systems, you have to cover it up with drywall. So if you're covering up with drywall, all you do is get a bunch of warm and fuzzies. Yeah, the building's made of wood, but we covered it all up with drywall. Duh. You know, it doesn't make sense. So what we're doing here is allowing you to use the beauty of wood and show wood, okay? Now, the 80% rule here, the 80% rule on this is that 80% of the ceiling space can be exposed wood. 20% has to be non-combustible. So that's drywall and the bottom plates of the composite beam. Aha! So now I can start to see how it's coming all together. We'll show you more about that in a minute. Balcony connections. Okay, we can incorporate cantilever pans into the composite beam slim floor with no problem. And we'll show you that in a minute. This here is very difficult to accomplish, very expensive. There's a lot of prototypes being built to try and work around what we can do with cantilever pans. Speaking of cantilevers, here we go. So what you see here, out to the street and off to the side. So you have a two-way cantilever here. Okay, this is a composite pan right here. So here's a curved pan right here. Okay, I'd like anybody in your audience here, can you tell me what kind of a connector that is? Anybody know what that is? Have you seen that before?
I don't think so.
That is a Gerber connector. And we use Gerber connectors throughout the building design. Now, a lot of structural engineers don't like Gerber connections because they're difficult to do the calculations. But because we've been doing it for 30 plus years, I guess we get good at it. Okay, so that's going to come back in a couple of moments. So I want you to think about that design right there. Yes, I know this is a very busy chart. Okay, now this was put together last week by my associate Luke Gagnon, who is the mass timber expert within our company. Now, what happened here is actually Luke met Sadar on Tuesday. Yeah. Now, what we're doing here is comparing point load system. So here's your bay area right here, about 600 square feet. Now, point load supported system turns out to be about $15 a square foot. Composite beam design is about $10 a square foot. So composite beam design is about 2/3 the price. So that makes quite a bit of difference on building design. So what you're doing here, so this is from drawings that were submitted for a project review in Washington, D.C. Okay. Now, when I was a young pup, and I did a lot of fireproofing with a company called W.R. Grace, we quickly learned that we had to keep the temperature of steel around below 1300 Fahrenheit in order to meet the building code. Because at 1300 Fahrenheit, steel gets plastic. Now, if you look carefully here, you can see the steel is not protected. So you see this bottom plate here? That gets plastic. So we worked with ULC and ULI to modify their fire testing, CAN ULC S101, to accommodate this flexibility here. Now, why is that important? Well, because this bottom plate supports the deck initially, but as you'll see, that support's not required once the whole deck assembly is put together. So here is the testing right here. We did the 1 hour beam test, passed the 2 hour test. The 2 hour beam passed the 3. The 3 hour beam passed the 4. So we never had to test our 4 hour beam because we got it with 3. So we have up to 4 hours on the beam alone. How that's achieved is evidenced right here. So what you see here, you have a hierarchy of connections between the beam and the deck, regardless of whether it's mass wood, long span metal, or hollow core. Okay, so here you can see these holes are for the transverse rebar that I showed you earlier on. And these holes here are completely filled with concrete, and the concrete surrounds the fire rebar. And you can see here we have a downturn buildup. So this whole area is completely filled with concrete. And as you well know, concrete becomes a tremendous heat sink. So the heat that's generated from the fire below is absorbed in this assembly and vented out through the top here. And that structure can survive for up to 4 hours. So now we did a test here showing what happens in a 1 hour fire rating. We were testing the connection between the wood deck and the beam itself. So we wanted proof of concept. So here is the deck assembly. This is CLT. You can see it doesn't look all that great, but that's what we used. Okay, so you have the CLT deck here. We also tested loading on another assembly. And if you look carefully here, there's no bottom plate. So what we're doing is using 3 plies here. We're testing the loading to make sure that the loading works properly, which it did. And then we actually did the burn. So here the fire is burning at the rate of about 1.5 inches per hour, about normal. And you can see here the beam is glowing red hot. Over here, after the 1 hour, this is what the assembly looked like. Now, if you look carefully here, we're showing you here that the wood actually charred less around the beam than around the rest of it. So that's a significant fire design note that was observed in Europe, and we see it happening here in our fire testing also. And again, here is a picture showing you the testing. Now, what happens here, so you can see how the load of the deck is transferred to the beam. So you can see the loading curve comes down here. So the massive part of the load rests right here on this. And it's also supported by the concrete interaction between the wood and the beam and between the rebar and the beam. So all of the loading is right here. So if that wood chars away here, that does not affect the loading of the deck. And you can see here, this is the bottom of the beam right here. And you can see the char rate drops significantly as it gets closer to the bottom flange of the beam. Okay, let's move away from fire and let's go back to some of the design notes. So as I mentioned earlier on, we use Gerber connections, and a lot of the connections are done across the tops of the beams, or tops of the columns, not the tops of the beams. Well, actually, top of the beam, come to think of it. So what you see here, it's a simple system. The columns are bolted to the floor or to the deck below or to the footings below here. And you can see the loading for and the fastening point for the next column. So we do all the design. So we make you look good to your instructor so that your project gets passed by the architects. So if you are structural engineers, this is how we make you look good. Now, non-composite is not very common. We see it not being used nearly as much as it used to be, particularly in Europe, because we've got a lot of issues with fire in that. And so you can see here what we've done to accommodate non-composite design. We have to router out this area. So yeah, what we did is send the Jolly Green Giant up with its king size router to take this area out. And here's where we put transverse fastening rods that fasten the deck to the beam. And then this whole area is going to be filled with cement. So just like a fish. So you have the main beam here and you have side beam coming off here. So the core of the fish is the steel right here. So we're using the analogy of the fish. Now, remember I mentioned earlier on the deck design. So here's a composite deck, TCC deck here. So you can see the beam. You can see how the column is fastened to the beam. Pretty simple construction, but very fast to erect. And there's a lot of tolerance built into that. So you can see here, what we're doing is beefing up that beam right there to carry the load of the building, because the load of the building goes right through the beam. But that has a limitation, and that's about 18 stories. Okay, so we have also done a lot of work on the research associated with this. And these white papers here show that we have done our research throughout North America and Europe to prove that the design concept is mature and is working in all cases. Now, we won't get into this much, but we've done a lot of work, again, in various methodologies. And this is the one that we find that proves this concept to be a valid engineering principle. Okay, one of the hallmarks of composite beams is this idea of long spans. Now, in Victoria, are we going to get a beam that's 25 meters long like you see here? Probably not, because it's very difficult to ship. This is in Saudi Arabia, where they don't have a lot of trees. But what that translates then is to what you see right here. There is no parkade in Victoria or Langford that has 4 parking stalls between columns. There are none, because they're all 3. So here you have bays that are 36 feet apart. And you notice here, mechanical, electrical, plumbing can go wherever it needs to go. So there's no beams or anything else, any obstructions that these plumbing has to go around. So the coordination between mechanical and structural is less rigorous. Now we have to go to hollow core for a moment to show you some cool design principles right here. So what I'm showing you here, bracing is part of our scope now. So we do the bracing, we coordinate that with you. So if the buildings have to be braced, then here's how we do it. So that's part of our design assist process. So the end result then, columns that are 36 feet apart, you can see mechanical, electrical going wherever it needs here. Now, what you don't normally see here is right here. Look carefully at that beam. You notice that's arched? Yes. It's arched here for a very good reason. Slope to drain. Because every other parkade in Victoria has to have slope to drain, and that water drains to the center because you have slope from the edges to get your 2% grade. So instead of doing it like that, what we do is that we put a trench drain in along this line right here, and we take one of the hollow core sections out, and that becomes the trench drain. So we're using far less concrete, and the excavation into the ground is far less. So you notice there's no beams. So we're saving 2 feet of excavation per floor when you do that kind of a situation. Okay, just as a summary here then, timber concrete composite, these are some of the attributes that building owners are starting to realize now, and this translates back to structural engineering, because this makes structural engineers' design criteria far easier to work with timber concrete composite. Okay, so more and more design is going this way for hybrid buildings. Just to show you that we've done a lot more testing, and we're doing testing all the time. In Europe, we have what we call the 90-minute test. In North America, we have to go to 2-hour test. So we have the assembly all set up, and we're going to be doing a 2-hour burn with ULI in Chicago sometime early fall to have a 2-hour ULI listed for composite beams and CLT deck. Oh, I'm sorry, composite beams with a TCC deck based on CLT as the core part. Okay, transverse reinforcement then. Here's how it's done, tying the deck to the beam if it's a straight non-composite deck. So this is how it's all comes together. Edge beams, if you have to do it this way, here's how we did it. So all the testing, all the prototypes, and there's been many examples in Europe using this kind of design principle. So back to some nice pictures. What we have here is the hallmark of composite beam design mass timber. So you can see here, composite beam going through. The architect likes my beautiful gray color here. And you notice the spacing here, 9 by 9. And you can see here, we cut grooves into the deck. Now this is an older system also. It's more modern than what I showed you originally with all the stirrups and that. But the limitations of this groove here is now being recognized. And so there's a lot of design modification required to make this more acceptable. And Sadar and Luke came to the conclusion that maybe we have something that's even better than that. So what we're doing is introducing a new connector here. Yes, it looks like a gang nail. And what it is a specially designed plate that's hammered into place here to take the lateral load of your deck design. So you can see here, the mesh is put on top of the connector here, and the concrete's poured right on top. So this is a fast economical system. It was introduced in Europe, and it's been used in many parts of Europe now, and it's just looking for the right opportunity to be used here in North America. We've done all the preliminary studies that indicate it's performing far better than what we had originally anticipated. But we have to do all the testing with North American wood, North American concrete, North American steel. So it's quite a bit different from Europe. So what is done in Europe has a direct application here, but you cannot always take one product and substitute into our design process here. We have to go through these steps to prove it, to make sure that it works under all conditions in North America. So we're doing that with some other designs right now. And whether that comes to fruition or not, we'll see down the road. But these are some of the other concepts that are all coming together pretty quickly in advanced mass timber design, because the connections between the column and the beam is where the huge expense is. And especially in seismic, we don't know all the ramifications of that yet. Now, tolerances, we'll show you tolerances here, but in vertical tolerances, here's what happens. So all the drawings start as CAD on your computers, and they go to various manufacturers. So you can see here what we can do with the composite beam going through a vertical CLT shear wall. Notice here that tolerance, we're talking millimeters there. So very tight. So now, what we're looking at here is our process. How we like to be involved with structural engineers throughout North America is right here. Structural engineers and architects. So if you have a project that is a twinkle in your client's eyes, here's when we like to be involved, right here, right at the preliminary project information. So if it's a design concept off the backs of napkins, we can do that. And we've done that with RJC, with some of their jobs on the Vancouver Island. Oh, I should mention too, if you want to see composite beams being installed, you can go up to Cowichan Valley High School, just about an hour's drive north of you, and you can see delta beams being installed. Forgot all about that. Okay, so what happens here is that we work through design process with you to determine if composite beams can be of value on your project. If you like what you see, then we issue a formal quote based on the drawings here. And if the offer gets accepted, then we make you, as structural engineers, we make you look good to your client. So what we're doing here is advanced 3D modeling, shop drawings, and we have people coming out to the field to supervise the actual installation. And that's exactly what happened when Sadar met with Luke Gagnon, my associate, because Luke was out from Quebec City to supervise the installation of the composite beams and the cementing of the beams in place. So that's tremendously important, and he will be out again to supervise this at certain steps throughout that process. So this is not a case of love you and leave you. This is a case that we're in it for the long haul. And here's an example of that right here. This is a high-rise tower in Winnipeg. It's actually the tallest tower in the world that had composite beams here. And so this is a success story because originally the building would not have gone ahead had it not been for composite beams and hollow core, because the original design called for cast in place at 32 stories. However, the developer could not make the job go at 32 stories, and so they had to change the design. So this was a success story. So now people on the top floor of this project here can sit here and watch their dog run away for 3 days all the way to Calgary. That's a prairie joke, by the way. Okay, so now I want to divest and come back to what we were talking about with mass wood. So you can see here, remember I showed you that Nilco connector? Well, these are older connectors here, but what it's showing you, this is slightly older technology, but we see here these screws, they are very difficult to install, and other trades come in and they come in, and what happens here is that they bend over the screws. So that's why we're trying to migrate away from that with Nilco. Now here, you can see this gap. This is going to be filled with concrete here. right here, and you can see the rebar. So these are various ways that the timber concrete composite deck is tied the concrete to the wood. And you saw these are older ways now, and you saw the Nilco that is looking to replace this. Okay, here's what we submit for review. Here's our shop drawings here. The shop drawings are issued in the province where the job is. Now I know this is you can see here. So they're stamped, and then we issue site drawings like what you see here for the erector and contractors. So a complete documentation package, a complete supervision package is issued for each job. So now also, I've showed you a lot of pictures where the beams are clearly evident in the design. Whereas here, what we're doing is showing you that some office designers don't like that wood look or don't like the steel look. So yes, you can have a clear space like what you see here. So clear open office space. Now let's look at a case history. So this is a project that's starting to come out of the ground right now. So this is UBC Gateway. Now this project is built on First Nations territory that has been unceded. So the designers, in this case Perkins and Will, wanted to make sure that the design of the building honored the First Nations legacy. And that is design it to make wood look good. So what you see here is the design concept that has been put forward, accepted, and is now being built. So what you see here is wood. You don't see any steel, and you see a very little concrete. Okay, but what you're looking at is right here. See these black lines here? That is composite beam design right there. So there's our composite beams right there in that project. Okay, right along here also. See this here? Now, what is interesting about this building is that there are life science labs here in this project. Now, life science labs, it is in the design of these types of buildings, life science labs require no vibration, essentially what it is. Okay, IIC, STC, and NRC are all higher than normal offices. And what they've done here is accommodate that design requirement, L over 600, L over 800 in some parts of the building here. So this beam design here is exceptionally stiff. And as a matter of fact, we have issues with some engineers who complain that the beam is far too stiff and they don't believe us. So here is the section here. This is called CRE. It's a CRE panel system that incorporates composite beams, delta beam, as a core part of the structure. Now I'm showing you this. This is a fairly complicated drawing, but it shows you the glulam beams here. And then you can see here the composite beam design right here and the rebar here. So call it concrete here. So concrete and steel to make wood look good in the core part of the building. Now here, what we have are all the EPDs. So if you have clients who are concerned about EPDs for environmental, whether you're dealing with LEED or Cascadia design criteria, all of the documentation is here through one click. Now, I show you this picture here. It's a mundane building, downtown Vancouver. It's a storage building. Now, why would I show a storage building? Well, in this case here, with storage buildings, well, with any building type, we have what's called FSR. An FSR rating is a measurement of the ratio of floor service ratio to the area of land. Now, in case here, this building had a height limitation of 100 feet. Now, what happens here is that when the original designers came along, they said, you can only get 5 floors. Well, that made the FSR about 3.5. Well, the developer said, I can't make that job fly. I can't get enough revenue from that building to make it a viable proposition. I need more space within that building because they had drop beams supporting hollow core. So the designers went back and said, okay, what we're going to do is replace it with composite beams in the structure right here. If you look carefully, you cannot see any beams there. Right here, you cannot see any beams in that ceiling space. So they were able to eliminate all the beams and have them all in the floor assembly, just like what you've seen with mass wood. And that enabled them to get another floor in the same building height. So they added one more floor, and that got the FSR from 3.5 to 5. Okay, I'm just going to take a short break here. And this is a video that my little buddy Peikko has been really anxious to show you. So we're going to come back in just after a minute or so and do a wrap up of the webinar. So here we are. Come on, Peikko, take it away. So there you have it. That's the overall summary of what DELTABEAM can offer you as the design engineer on your projects. So what you see here, you can see the DELTABEAM Select. That's a free tool. And if you'd like, we can possibly run a webinar if you wanted to use that as part of your design, if you're looking at that for your assignment. So there's a number of white papers that are designed to help you understand the concept and work with it for its maximum efficiency. Also, too, I should mention that in my signature that I write out all the time, Sadar has it, there's a link at the bottom of my signature that shows you another video, and that video is designed specifically for slim floors, predominantly for education buildings such as schools. So where we've been today, we've talked about the niche that we see for composite beams, where it's going to be really beneficial for building owners. I've talked about the installation steps and some of the cost comparisons, fire design, and the technical considerations that you have to think about. And then finally, we defined our scope of work and presented some case history on projects that are coming together right now. And see, even this webinar was put together earlier this week, and now it's already outdated by a project that's taken place in your backyard up in at the school. So back to you. Questions, comments, concerns? Any questions from you, the group? I'm sure you have some.